Welcome to the Swayam Prabha series in computer science. In this series, this is a course on artificial intelligence, and continuing from the last class where we dealt with the neural networks, today we are going to see how embeddings are created using neural networks. And if you just have a quick recap of the last class, that is on NLP. If you look at embeddings, we saw it was dense, and the sparse vector was for one hot encoding, but then we said it will occupy more space and there are disadvantages with one hot encoding. So, we will go in for dense vectors, and which are low dimensional vectors, which are embeddings. And we also saw words that have similar meaning that are very close in vector space. We saw a few examples of that in the last class, and that has the distributional hypothesis. And we also dealt with two types of say the embeddings. One was CBOW and continuous bag of words, and skip gram counting. We saw an examples of both, and today we will see deeper into that. Like for example, if you have a word called king, how is it getting converted into numbers like 0.25 minus 0.61 and 0.88? How does it work? Last class we saw only the application. Okay, we assume that there are some numbers and how it is closer in the vector space. So, today we will see how to compute these numbers and how it is actually placed in the vector space. There is a king and suppose there is queen, the vector space would be say 0.35 minus 0.59, 0.89. Suppose if it is closer, we will say that these two are going to be closer in a vector space. How does it, how is it happening? So, if you look at the entire flow of how the computation is happening, it is through the neural networks that we discussed in the last class, where you have the corpus, which is a set of all the natural language sentences, and here we are taking only the English, but it also includes other type of languages also, natural language sentences that consists of the corpus. And we have the training pairs, for example, skipgram. If you take the last example, the cat sat, the cat, this is one training pair, cat sat, another training pair. And with these training pairs, and here this is an example, but in reality there can be a number of training pairs. It can be the cat and then it can be sat. So, we can have number of training pairs like this, and having these training pairs we will pass into a tiny neural network. And why it is tiny neural network? Because we will have only three layers. One is the input layer, one for the middle layer, and one at the output layer. And then we will compute the loss. Loss is from the output layer side. And suppose the idea is, if you have the input layer and the middle layer and the output layer like this. Suppose we have the input as we have to predict the output as cat. So, that is our task, and for this task we will see what is the loss after passing through the neural networks. And remember, it is going to be W transpose X, pass on to the activation function Z, and from here go to the softmax layer, get the probability, and at this region we will get some value here, and that value, through that value we will calculate the error, and that error or the loss, what is the loss that is available. And ideally we would like the loss to be minimized very close to 0, which will be approximately should be equal to 0, but it will not happen. And how do we reduce this loss? Through the back propagation method, again that we discussed in the last class. And once we do this a number of times, repeat the whole structure here with a number of times, we will get an updated embeddings. And where does this updated embeddings happening? This is embedding happening at these weights. So, this process of updated embeddings and how we arrive at the embedding we will be discussing in this session. Let us take an example. This is an example that we take, the cat sat on the mat. So, similar example, if you see the vocabulary, this is 1, 2, 3, 4, 5, there are 6 words, but the is repeated. If you see the is repeated, and we will take one more. So, we are taking only one the instead of it, and apart from cat we will also say dog, and we will see why cat and dog are very similar vectors towards the end of the session. So, apart from this, so we along with dog now we have the vocabulary to be 6, and assume that we have the embedding dimension as 3. So, there are 3 points that we need as weights, and let us take the skip-gram model where the window size is 1, meaning if it is the, it has to predict cat, and if it is cat it has to predict sat, it's like that. So, we have the index, suppose the word is the cat sat on mat dog, and the index for each of the word is given as 0, 1, 2, 3, 4, the dog is 5. And given these index, now let us do a one hot encoding where the and because it is 6. So, you would have the 6 bits 1, 2, 3, 4, 5, 6 bits, and the stands for the first position, cat for the second position. This is the index because the index we have seen here, the same index position is coming right here, 5 for mat, dog for 6. Now, these they are actually useless on their own. Why? Because these are equally distanced. How is it equally distanced? Because if you say dog and cat, these are very distant. If you take the cosine similarity of these two, it would be 0. But we know that cat and dog are going to be the animals and they should share the same vector space. So, how are we going to bring those closer together is what this session is all about. Let us say before moving into how we calculate, let us target the skip-gram with window size 1. Here we have the position which is the 6 positions each standing for the sentence. What is the center portion, the left and the right? Suppose for example, the center is the, I am just writing, the cat sat on the mat. So, if this is center, the left of it is nothing, on the right it is going to be cat. So, the pairs generated will be the cat. If you take the next window, this is the first window, this is first window, the second window is cat sat. So, the center is cat, the left is the right is sat. So, we have 2 pairs generated, cat, the cat sat. And similarly, the third, I will take one more example and then move on. Let us take the third one, this window, sat on, the center is, if the center is sat, the left of it is going to be cat, the right is going to be on. So, there are 2 pairs generated, sat cat and sat on, and it moves on to the next window and the next window, and the last window if you see mat and then nothing. In this case, mat is at the center, the is towards the left and nothing towards the right. So, there will be 1. So, the number of pairs that are generated are going to be 10 training pairs, and the formula is n is going to be the number of words. So, 2 into n minus 1, which is 10. Now, what we will do is we will take only one pair and see how the training is occurring. So, let us take cat sat, let us take this, the center is cat and the right is sat. How does the training occur? So, this is a skip-gram that we are going to follow, where the X region is 6 dimension 1 hot vectors that we have seen here. This is 6 dimension 1 hot vector, that is X. So assume that there are 6 vectors, for each input is for one word, and there are 3 neurons. So this weight, the weight of at this stage, it is going to be X6 cross 3, 6 inputs and 3 neurons. So the H is going to be the hidden values that is coming out of these neurons. Then at the other side we will have 6 output, each for the word. Why? Because when we say the, it has to predict cat, and when we say cat, it has to predict sat. So this is our task. So at this region we will have 3 cross 6, 6 cross 3 dimension and 3 cross 6. At this stage we will get 6 cores, each for the value, and for this, after getting the 6 cores, we will use a softmax function to find out y cap. Y cap is the output of the neural network that we get at the end. So W is going to be the input embedding matrix, which is at this region, which is our maximum importance. Each row is embedding of one word. W dash is going to be the output embedding, where each column is going to be the context vector. And after one training, we will keep only this, the left portion of it is W, which is the embedding, and throw away this W dash. So let us take one example and we will go through the entire flow for this example. The first, let us take the first one where the initialize W. W is 6 cross 3, where I set this region. There are 6 inputs and 3 neurons. So it is 6 cross 3. This weight, we are going to start with random values. Let us take the, which is this is the index, 0, 1, 2, 3, 4, 5 is the index, and for the vector is 0.1, minus 0.2, 0.3. For cat it is 0.5, 0.1 and minus 0.4. And why this is highlighted is, this is the given vector. Given cat, we have to predict sat, and after one update or 2 updates or multiple updates, we want to see cat and sat, the loss is going to be minimized, and there is the prediction is going to occur. Highlighted is the cat's embedding. So the W cat is 0.5, 0.1 and minus 0.4. At start, these are the random values, any values we can take, but after updating, these value might change. And remember these values. Now we will initialize W dash. W dash is the other side. See, remember this is X, we have 1 to 6, and that we have 3 neurons, and from 3 neurons again we have 1 to 6. So this is 3 cross 6 and this is this is 6 cross 3 and this is 3 cross 6. So this W dash we are assigning as row 1, row 2, row 3, which is for this vector. For this particular point, these are the values that we have. For cat, these are the values we have. Okay. And these values again are random in nature at the beginning. These are random. And suppose we take the third point, which is sat, third vector here. Sat, these are the values at start, 0.3, minus 0.1 and 0.4. Now forward pass, it is the same method that we did in the neural networks, where we are going to calculate W transpose X, or in this case it is going to be X transpose W. It is nothing but we are multiplying and W with X and summing up those values. So if you see the cat, given cat, we have to predict the target context as sat. So the cat is given as 0, 1, all these zeros, and the value of W for cat is going to be 0.5, 0.1 and minus 0.4. Now when we multiply this with this x transpose and w and adding that, we will get the same result. Why? Because the other things are going to be 0. Now for each word we will be calculating uj. U is at the end output, and remember when we had 6, 1 to up to 6, and we had 3 neurons, and at this side we had 1 to up to 6. So this at this stage it is H, and this stage it is U. So U is at the other end. What we got the value as H, the H is at this stage, and U is got at this stage. So U is H with multiplied by W dash. W dash is going to be the weights at this region. W is the weights at the first part. W dash is this part. So if you see W dash here, the value would be, if you just calculate for this alone, the same calculation is going ahead with the same type, H multiplied by W dash, 0.5 into 0.3 plus 0.1 into minus 0.1 and 0.4 into 0.4. Where did we get that? This 0.5, 0.1 minus 0.4 is coming from H. These values are W dash weight. Multiplying those W dash with H, we will get U as 0.02. That is, suppose we have the output as CAD SAT. Suppose at this point the SAT, the value at this word we get it as minus 0.2. Now at this minus 0.2, so this is the value. U at the output is these values 0.11, 0.21, 0.02 and other things. This is the softmax region. Softmax is, we are taking the exponential of each value divided by the summation of the exponential of all the values. So we sum up of all the exponentials, which is 6.017. So 1.116 divided by 6.017, we get 0.186. This is the softmax output. At the softmax output, if you take only SAT, why we are taking SAT? Because our domain of interest, our interest is given CAT, what is the probability that SAT is predicted. So if we take this SAT value, we get the softmax probability as 0.163. The meaning is, given CAT, predict CAT with probability is 16.3%, but we want this number to be higher. We want, ideally it is to be close to 99% or 100%. 100% will never occur, at least can we get 99%, and what is to be done in order to go from 16.3 to 99%. So for that we will do the back propagation method, and before that it is going to be the loss, and how the loss is calculated, because we know at this point for SAT it is going to be 0, 0, 1, 0. This is the target value for SAT. The entropy, cross entropy is minus logarithm of 0.163. Where did we get 0.163? It is the output of the softmax. We get the loss as 1.814. This loss is actually more. The loss we need, ideally it is to be close to, ideal target should be very close to 0. It should be moving to 0. We will not be, should not be 0, but at least be moving to 0. So here this loss, it is actually large and it is not confident about SAT. So we want it to move towards 0. So our job is change W and W dash so that the next forward pass gives a higher YSAT value, which means it will be less. So how do we change W and W dash? Again it is through the back propagation method. And the back propagation method, let's take the dou L by dou U. Dou L is for the loss and U is the output side. Y cap is what we got at the output and Y is the target value. So if we have dou L by dou L Y value, Y cap minus Y, this is the error. This is the error that we get. And if you see for SAT, we got Y cap to be 0.163. Remember from the previous slide, we got 0.163. Ideally, this should be 1. So what is the error that we have? It is 0.163 minus 1, which is minus 0.837. For all the other values, if you see, it is positive values, and for SAT it is going to be the negative value. The interpretation is negative at SAT, we want to push the score up. Positive elsewhere, we have to push that down, and that is done by our gradient function. The gradient function would be dou L by the loss by weight, where Y cap minus Y multiplied by H, the loss multiplied by H value. And if you see that, it would be minus, the error is minus 0.837 that we got from this point. And error multiplied by H, we get these values 0.419, 0.084 and 0.335. So this is the value that we get after this gradient value. Now given that, what will happen to the cat, the previous weight value? This is for W dash, and here this is for W, dou L by dou W of cat. The previous, if you look at the neural network side, we have W as one region and W dash as the other region, and between you have 3 neurons. Now we were talking about W dash in the previous slide. Now we are talking how to change the weights for this region. So here we have the error of minus 0.837, and this is the column value of W dash. We multiply it, we get these values, and adding up all these values, the same thing goes here, 0.186 with W dash. W dash is the same that we had, this is a random value we started off with. We multiplied these both, we get these values. Now we add up all these values, we have minus 0.231, 0.175 and 0.317, where at this point, if you look at it, there is one neuron constituting the entire value of the sum from all the inputs. So this is going to play a role in updating the weight matrix. Now with these values, we are going to update W. So dou L by dou cat is 0.231, 0.175 and minus 0.317. Why does this sum come? Because look at minus 0.37, this actually dominates the sum. When you compare this minus 0.837 with all others, this is going to be dominating the sum value, and if you see, all these are going to be very less value and this is more. Therefore, this dominates the value. So the gradient of W cat pushes in the direction of SAT. If you see cat and SAT, the values are going to be very much similar. So this is exactly what we actually want. So cat and SAT, we started off with different values, but due to back propagation, these become more aligned. So this is what is happening with respect to backward propagation. Now SGD stands for stochastic gradient descent, and stochastic is update, where we have the learning rate as 0.1. Suppose we have 0.1. This slide gives the update of weight for both W dash and W. For W dash, this was our initial weight 0.3 minus 0.1 and 0.4 minus this 0.1 is the learning weight, and these values we got from the error values. Error with the gradient, we got this as a result, no? 0.1 into these values. So the resulting W dash for SAT is 0.342, 0.092 and 0.367. Now for cat, it is going to be 0.5, 0.1 and minus 0.4 minus this 1.1 multiplied by these values. So, we get 0.523, 0.083 and 0.368. So, if you see, we had 6 inputs, 3 neurons and 6 outputs, each representing for a word. Now, if we say we are taking only this cat portion here, and you can imagine the other portions also from the same thing. And here the cat sat is at this point, so it would be ideally at this level. So, if you see this value, earlier the value was 0.3 minus 0.1 and 0.4. Now, after the update, after one update, this changed to 0.342, 0.092 and 0.367. Now, if you look at this side, earlier this SAT was 0.5, 0.1 and minus 0.4. Now, it has moved to 0.523, 0.083 and minus 0.368. So, you can see that it has moved from 0.5 to 0.523. Yeah. So, this is what is being said here. The new H is these values, the new U, the output is this. Earlier it used to be 0.163 and after one update it is 0.172. So, you can see how the loss is also getting reduced and how these values are getting increased. So, and these are again the training and embedding. So, that we describe with respect to the output values. Here what happens to the embedding, where is the embedding hiding? It is only this region. The embedding is the first W part and after one update it moves to 0.523, 0.083 and 0.368. This is going to be the embedding values for cat. That is what is described here. For WSAT and dog it is nothing, but after a few iterations we could see that the dog and cat, it can have a similar cluster like kind of thing. So, and the loss we are not going to be completely 0 because the, suppose we take for example cat sleeps or cat purse. In this case if it is going to be 0, the entire would be 0. So, always we do not want it to be exactly 0, but it is a non-zero minimum. So, the embeddings are not, so we are not using the neural network to learn embeddings, but it is actually a byproduct of it where we see only at the W level. The first weight matrix is actually the embeddings. So, this is a quick recap of whatever we did as a pseudocode. So, for the entire epoch we calculated H hidden weight and U is the output, and from U we calculated using softmax Y, and the error we know the target value which is a supervised thing. So, error is Y hat which is a predicted one minus 1 hot, and we, through that using these two are going to be the back propagation, and through this back propagation we will be able to get the embedding and the prediction. Yeah. And then the summary in this session we have done two things. One is a prediction of one word over the other or one set of words over the other words, and other would be the embeddings. Given one pair, follow the forward pass, the loss, backward pass, and then the update, and repeat that a million times where we get the embedding matrix. So, in this session we completed embeddings, and in the next section we would move with another technique called globe, where we would again deal with some kind of embedding, and the common one that is used is BERT. Till then, thank you.